Hello, everyone. Today we are going to be talking about Chapter 5, Lecture 12, Learning Objective number 6. So we're going to be looking at our heat at a constant pressure, change in enthalpy, and looking at our signs of both, and from there determining if we have an endothermic or exothermic process. Okay, let's go ahead and get started with our enthalpy equation. So enthalpy, remember, is our heat, not our Q, but our state function for this. So this is usually expressed as a change in enthalpy. So this is our change in enthalpy. And if we have a process, we have H final minus H initial. So this is where we're different from our Q heat. So our enthalpy here, our state function enthalpy, only depends on our final and our initial states. And we can also get this in terms of energy. So our energy and our pressure volume work, which we did in the last video. So that idea of pressure volume. And here we're going to keep temperature constant. We're going to keep pressure constant. Our temperature and pressure are kept constant. So this is a constant pressure system. And here our work is only pressure volume work. And since we're keeping our pressure the same, our work is just the expansion and compression of a gas. Okay, so if we take that delta H, keeping pressure constant, we have delta E, our internal energy, plus P, because it's kept constant, so no delta, delta V. So here's our change in volume when we have a change in our internal energy, and that is what enthalpy is. So our enthalpy is the sum of our change in internal energy plus our pressure volume work. So now we're going to actually take this idea, one that we saw earlier, where work is equal to negative P delta V, okay, and delta E is equal to Q plus W. So our work in this case is our pressure volume work, right? And when we were looking at work earlier, and then our internal energy is work plus heat. So we're going to place this into here. This is going to be rearranged in negative W is equal to P delta V. So this will replace that. And what we get is delta H is equal to Q plus W minus W. So our enthalpy is equal to our heat, our Q, when pressure is kept constant. So we put a subscript P to indicate constant pressure. Okay? So the heat flow Q is equal to our enthalpy, H, when pressure is kept constant. Okay. So how are our signs going to determine whether we are exothermic or endothermic? So here, delta E, delta H. So let's do it down here. Delta E and delta H are going to be very similar. There's going to be small differences because the work done by a reaction very similar in value for a reaction. Because the work done in a reaction is only pressure volume work of a gas expanding or contracting, and that's not a lot. Okay, I'm actually going to put that on the next line. Significant. Okay, so just as a note. Now, let's look at delta H itself. So our delta H, just like our delta E, since they are very similar, if we have positive, then just like with our internal energy, our system has gained heat. So almost always this is a endergonic process, but when we're specifically talking about our enthalpy, we call this an exothermic process or endothermic process. So if you have gained heat, it is endothermic. If we have, I'm actually gonna, so as not to confuse, if we have a delta H value that is negative, our system has released heat. So this will be similar to an exergonic process. So we call this exothermic if we are talking about specifically heat energy. So releasing heat is exothermic. With reactions, we have looked at the um, internal energy of a reaction, but we're almost always going to be looking at enthalpy of reactions because we really care about that heat energy more than anything else. So our enthalpy of reaction, we get it as delta H reaction, and it's equal to our enthalpy of our products minus the enthalpy of our reactants. Okay, so this is the heat absorbed or released during a reaction. So the heat of a reaction. As a note, if we have a combustion reaction, something like this, CH4 gas plus 2O2 gas, going to CO2 gas plus 2H2O liquid. This will have an enthalpy value of per reaction. So that means that for every 1 mole of CH4 in the gaseous state that is combusted, negative 890 kilojoules of energy is released. So we could also write this as delta H equals negative 890 kilojoules per mole of CH4, or 2 moles of O2. Now, because our delta H is products minus reactants, are our products, these are our reactants. If we are to take the opposite process to flip this reaction, so CO2 gas plus 2H2O liquid goes to CH4 gas plus 2O2 gas, is going to be positive 890 kilojoules. Okay, so flipping a reaction, you're going to have the opposite sign because now your reactants are your products are your reactants. Take the states, these enthalpies are state dependent. So it does matter what state you're in. Different states will have different enthalpies of reaction. Okay, everything for this video. I will see you guys in the next one. Bye, y'all.